Hi, I'm Colin from the technical team at Crawford Scientific, and we today are continuing with our guides which are looking at products, everyday products that we use within the lab, which are essential but perhaps not the most exciting. And today we're going to be looking at gas filters for GC. So gas filters are the units that we place in line between the feed gases and the GC itself, and they are there to remove contamination. And the three main types of contamination that we are concerned with GC are water, organics and oxygen. And there are two main areas within the GC that are susceptible to contamination. The first is the carrier gas, and we want to make sure that the carrier gas has been filtered for water, organics and oxygen in order to protect the column. The second area of the GC is the detector. So there are numerous detectors with GC such as FID, NPD and ECD, which use gases in their mode of detection, and we want to make sure that the gases we use are pure so that we get a reduction in the amount of noise and we improve sensitivity. GC columns bleed all the time, but they bleed more under the following conditions. First is high temperature, and this is one of the reasons why we see a baseline sloping upwards in the temperature programme. Second is light, and that's why the columns are brown. This is a coating that is applied to the columns to reduce the amount of UV reaching the stationary phase. The third one is oxygen, and that runs the risk of oxidising the stationary phase, and the fourth is water, which hydrolyses the stationary phase bond. These days it's really unusual to see the gas cylinders sitting next to the GC, and mostly we have the cylinders which are quite a distance remote from the GC and are plumbed into the gas chromatograph using long lines of copper tubing. The longer the pipe runs, the more joins we'll have in that pipe, and the greater the risk is that there will be a leak. And it's almost expected that most insulation these days there will be a leak somewhere along the way getting the gas from the cylinder up to the GC. When we have a leak, there's a risk that we will introduce air into the line, air containing water and oxygen. If that's then being piped into the GC, particularly when we're running that at temperature, there's a real risk that we will accelerate the damage in the column. And one of the biggest dangers we have is when we condition the column, when we're operating it at close to its maximum temperature, when there is a small leak of air and oxygen coming in, and it's a very quick way to ruin a GC column. So it's important that we make sure the carrier gas line at the GC has been filtered to remove any oxygen and water. For the water filter, most manufacturers these days have standardised on molecular sieve 5A. So this removes water but also some organics. We would expect a typical unit to remove about 7.2 grams of water and give residual levels of less than 0.1 ppm. With the oxygen filter, this is often manganese based, and it also removes small organics and halogens. And typically we would expect it to remove about 150 mils of oxygen to levels of less than 50 ppb. But the oxygen filter is fouled by water, so we always place it last in the chain. When we're using very pure feed gases, very often for GCMS, we can use filters which have much lower capacity, and in that case we can use a triple filter, which is a filter that has combined water, charcoal and oxygen filters. And some of these also contain other adsorbents to remove as much contamination as possible. They have a relatively small capacity, so for oxygen it's about 100 mils of oxygen that they remove and only about a gram of water. And if one of the beds becomes exhausted, you need to change the whole filter, so they're not particularly efficient that way. Definitely designed for use with high purity gases, usually in GCMS, so we don't need particularly high capacity. They're simple and they are cost effective. We need to locate the filters as close to the GC as possible, ideally with only a short piece of connecting tubing to the GC. If we're using one filter stack for several GCs, and most systems allow you to operate up to 4 GCs from a single filter stack, we should arrange the plumbing such that we've got minimal pipe runs from the filter stack into the GC. We use activated charcoal as the filter to remove organics, and a typical organics filter would remove about 7 grams of impurity and purify to less than 0.1 ppm. But bear in mind it's not a panacea. There are certain compounds that the filter won't remove, and some of the more significant ones for GC would be formaldehyde, inorganic acids, carbon dioxide, although this is often removed by the molecular sieve, and ammonia. The order that we place the filters is also really important. The first in line is always the water filter, as this is the most common contaminant and it greatly accelerates the rate of degradation of the oxygen filter. The organics filter benefits from having water removed first as well, so the main order would be the water filter first, then the organics filter, and then the oxygen filter. Now, all the different manufacturers use different colours to indicate when the filter's been exhausted, but the indicator shows when the cartridge needs to be replaced. How often should we be expecting to replace the filters? Well, that depends totally on the number of GCs that you have plumbed into the filter stack, but more importantly on the quality of the feed gas that you're using. When you have a very high use rate of filters, the best solution is to try to improve the quality of the feed gas going in. Normally that would be to check for leaks in the system and to do what you can to try to patch the leaks, or to make sure that you're using a higher quality of gas. If that's not possible, then the next thing we can do is looking at using high capacity filters, and we very often see that the inline design of filters have a much higher capacity, and they are used without an indicator, and then we have a small indicating filter that sits upline for them. So the indicating filter is used primarily for the indicator and as a fallback of material that covers from the main inline filter being exhausted. We often see these days, particularly with helium, where the price of helium is becoming more expensive and also the availability of suitable high-grade helium is becoming much more difficult to source, that we see a lot of customers moving now to using filters to uprate lower grade of gas. And it is possible to do that, and we increasingly see customers using grade 4.6 helium, which is 99.996% pure, and then using filters after that to upgrade the quality of the gas to a level that would be suitable for GC and GCMS. Overall, it's usually cheaper to do that now because the cost of helium is so high. We will see a much higher attrition rate of filters, so rather than expecting a year out of each filter, we might be changing them as much as every couple of months. But the costs involved in replacing the filters, it's usually still cheaper than having to try to source more expensive grades of gas. Now, the manufacturers, depending on who you speak to, tend to indicate it's about 30% cheaper, even with a higher use rate of filters, to use filters but to buy cheaper, lower grade gas supply. The main detector types that use feed gases are FID and NPD, so they use fuel, which is hydrogen, oxygen, which is air, and makeup, which is either helium or nitrogen. Now, as these are air-based flames which produce water as the byproduct, then there's no advantage at all in using oxygen and water filters on any of these gases. However, we do need to ensure that the organic contamination is reduced to a minimum to reduce noise and spikes and improve detection limits. By convention, we use an organics charcoal filter on the hydrogen feed only. But if we're using makeup that's different from the carrier, you should also consider using an organics filter on this feed too. Most users don't use an organics filter on the air source, but you need to be really careful if you're using air supply which is very poor quality, such as from a general lab compressor. And if you are, it's then recommended that you should consider using one. ECD, electron capture detector, uses makeup gas, and this is normally nitrogen or argon, and ECD is particularly sensitive to the presence of oxygen in air and water. Both of these are strongly electron capturing, and small quantities will generate noise and poor sensitivity. So the makeup into ECD should always be filtered for water, organics and oxygen. So there are two main types of filter that we see. The first is inline, and these are cheaper as a single purchase because we don't have to factor in the additional expense of hardware, a base plate, in order to fit them. They're more flexible in where they can be placed, and they often have much higher capacities. The big disadvantage though is that we need to interrupt the flow when we replace these filters. And it's not just a case of the delay associated with interrupting the flow to replace the filter. We then need to purge the lines out after that, because when we fit the filter, we introduce air into the lines. And that can be often an overnight that requires to be purged to a low enough level that it doesn't cause a problem, particularly with GCMS or when we're working with high temperature applications. The second type, which are usually the most common ones that we see, are ones in which there is a base plate. So these are cartridge units that just slot into a base plate. You normally get a neater and smaller installation, and they can be replaced without interrupting flow. So we don't have that risk of introducing air when we need to change the filter. The linear path of the three filters is a much smaller, neater space than if we were to try to chain three inline filters together in a line. One thing to bear in mind is that all the filters, whether it's inline or cartridge-based units, are all supplied sealed with some kind of gas in there to protect the filter from external environmental contamination. It's normally nitrogen. So when we place the filter in, we need to remember that that gas will take time to flush through. And the main area of concern for that is when we work with the GCMS. So if there's nitrogen present in the filters when they're supplied, then what we will see is quite a high signal for nitrogen in the tune page for the GCMS for some considerable time after the unit's been changed. It's worthwhile considering purging the unit out to get rid of nitrogen if that's going to be a problem for us with GCMS. So there we have it. That was the latest thrilling instalment in our series. But I hope that was useful to you, and thanks very much for watching.